At the end of this session, students should be able to identify whether a mixture of reactants is stoichiometric or not, identify the limiting reactants in case of non-stoichiometric mixture of reactants, determine the quantity, number of mole in mole, mass in gram, volume of a gas in liter of a product formed or of a reactant disappear during a chemical reaction. And finally, define and calculate the yield of a chemical reaction. Part 1. Stoichiometric and non-stoichiometric mixture. How can we identify if a mixture of reactants is stoichiometric or not? Given the general equation, AA plus BB gives CC plus DD, where small a, b, c, d are the stoichiometric coefficient, and at t equals 0 we are given initial number of mole of A and initial number of mole of B. This is the initial mixture of reactants, while C and D the products in N equal 0 at the beginning of the reaction. In order to determine if the initial mixture of reactants is stoichiometric or not, we should calculate the ratio for each reactant. For A, ratio of reactant A equal N0 of reactant A over stoichiometry of the reactant, which is A. And for B, N0 B over B. We have two cases. If ratio of A equal ratio of B after calculation, then the initial mixture of reactants is stoichiometric and the two reactants are limiting. That means at the end of the reaction, in this case, number of mole of reactant A and number of mole of reactant B equal 0 because they disappear completely since they are limiting reactants. But if ratio of A different than ratio of B, then the initial mixture of reactants is non-stoichiometric. In this case, also we have two cases. If ratio of A is less than ratio of B, then A is the limiting reactant and B is the reactant in excess. If ratio of A bigger than ratio of B, then B is the limiting reactant and A is the reactant in excess. In case of non-stoichiometric mixture, the reactant that has smallest ratio is the limiting reactant. That means it disappears completely at the end of the reaction. While the reactant that has the bigger ratio is the reactant in excess. That means it does not disappear completely at the end of the reaction. Two, chemical calculation. Part A, calculation of the number of moles. According to the stoichiometry of the reaction or stoichiometric ratio of reaction AA plus BB gives CC plus DD, we have number of mole of A reacted over stoichiometry A equal number of mole of B reacted over stoichiometry B equal number of mole of C formed over stoichiometry C equal number of mole of D formed over stoichiometric coefficient D. In case of non-stoichiometric mixture of reactants, we use the limiting reactant to calculate the number of moles of other components of the reaction mixture. That means if we have one reactant is limiting, the other is in excess, in order to determine the number of mole of products formed or the number of mole of the excess left or reacted of the reactant in excess, always we should use the limiting reactant in the calculation. For the limiting reactant, number of mole of reactants is equal to the initial number of mole, since the limiting reactant disappears completely. Then N0 of this reactant react completely. For example, if A is the limiting reactant, the relation becomes N0A. We replace NA reacted by N0 because number of mole of A reacted equal N0 since it is the limiting reactant. Then N0A over A equal NB reacted over B equal NC formed over C equal ND formed over D. And then we can calculate the number of mole of B reacted using N0 of the limiting reactant. The same for product using always the N0 of the limiting reactant. To determine the number of moles left of the reactant in excess, first we calculate the number of moles reacted using the relation N0A over A equal NB over B, then NB reacted equal B cross multiplication over A. And B times N0A over A. N0A is given, B and A are stoichiometry of the reaction, then we calculate number of mole of B reacted. Then we calculate the number of moles left based on the relation NB left equal N0B, initial number of mole B minus number of mole reacted, we deduce number of mole left or remaining. Now, calculation of the mass. After we have calculated the number of mole of reactant disappears or product formed, reactant left for reactant in excess, we can reduce the mass and the volume. For the mass, to calculate the mass of a reactant or a product, reactant left or product formed, first we calculate its number of moles based on the stoichiometry of the reaction, as we have seen in the part A. Then we calculate the mass based on the relation. We have number of mole equal mass over molar mass, then mass equal number of mole times molar mass. Calculation of the volume of a gas. If we have a gaseous reactant or product, we can deduce its volume. To calculate the volume of reactant left or of a product formed in gaseous state, first we calculate its number of mole based on the stoichiometry of the reaction, as we have seen in part A. Then we calculate the volume based on the relation. Number of mole of a gas equal volume of gas over molar volume. Molar volume is a given, 22.4 liters per mole at CNTP or at STP, or 24 liters per mole at 25 degrees. It is always given. Then V equal number of mole times molar volume. This is the calculation of number of mole of mass and volume of gas. Now, yield of a chemical reaction. The calculated quantity, number of mole, mass, or volume of gas of product based on the stoichiometry of the reaction is the maximum quantity that should be obtained. That means the theoretical quantity. Theoretically, we can obtain the calculated quantity based on the stoichiometry using the limiting reactant. But experimentally, at the end of the reaction, the quantity of the product obtained could be equal or less than the theoretical quantity. Therefore, the yield of a chemical reaction is the ratio of the quantity of product obtained experimentally, which is the actual quantity, over the quantity of product obtained theoretically, which is the expected quantity. The relation yield equal experimental quantity of product over theoretical quantity of product. The quantity of product could be in mole, then the yield of the reaction becomes yield equal number of mole product experimental over number of mole of product theoretical, or number of mole product actual number of mole of product over expected number of mole of the product. The same, experimental or actual, theoretical or expected. If the quantity of product is in gram, then the yield of the reaction becomes mass of product experimentally over mass of product theoretically, or mass of product actually over mass of product expected. If the quantity of the gaseous product could be in liter, if the quantity is in liter, then the yield of the reaction becomes volume of product experimentally over volume of product theoretically, or volume of product actual over volume of product expected. This is the yield of the reaction. Application. In a beaker of 250 milliliter, we pour a volume V1 equal 100 milliliter of an acidified solution of potassium permanganate, KMnO4, K plus MnO4 minus, of concentration C1 equals 0.01 mole per liter. At the instant T equals 0, the instant of the starting of the reaction, we add a volume B2 equal 100 milliliter of an oxalic acid H2C2O4 solution of concentration C2 equals 0.1 mole per liter. The net equation of the reaction, 2MnO4 minus plus 5H2C2O4 plus 6H plus, gives 10 CO2 plus 2Mn2 plus 8H2O. 1. Show that oxalic acid is in excess. That means MnO4 minus is the limiting reactant. Determine the volume of CO2 that should be obtained at the end of the reaction. That should be obtained, that means theoretical, that means calculated based on the stoichiometry of the reaction using the limiting reactant. C. Deduce the percent yield of the reaction, knowing that the volume of CO2 obtained at the end of the reaction is V equal 110 milliliter, where the molar volume of gas equal 24 liter per mole. Then we are given the experimental, we are given the experimental volume of product. We need to calculate the theoretical volume in part 2 to deduce the yield of the reaction. Solution of application 3. We should calculate the initial number of mole for each reactant to deduce the limiting reactant and the reactant in excess. Always we use the initial number of mole. N0 of MnO4 minus equal N0 of KMnO4, because each KMnO4 compound, iron compound, we have one permanganate ion, equals C1 times V1, C1 equals 0.V1, and volume 100 milliliters, that means 0.1 liter, equal 110 minus 3 mole. N0 of H2C2O4 equals C times V, 0.1 concentration, 0.1 volume equal 10 minus 3 or 110 minus 2 mole. We calculate the ratio for each one reactant. Ratio of aminophore mass equal N0 aminophore mass over stoichiometry, which is 2, based on the equation, equal N0 10 minus 3, 110 minus 3 over 2, equal 5 10 minus 4. This is the ratio. Ratio without unit, the ratio is without unit because mole over mole, stoichiometry in mole. Ratio of H2C2O4 equal N0 H2C2O4 over stoichiometry, which is 5 based on the net equation. Number of mole 10 minus 3 equal 10 minus 2 over 5 equal to 10 minus 3, the ratio of H2C2O4. We compare the two ratio. We find that 2 10 minus 3 bigger than 5 10 minus 2, then ratio of H2C2O4 bigger than ratio of H2 aminophore minus this, then H2C2O4 is the reaction axis and aminophore minus limiting. Ratio of aminophore minus less than ratio of H2CO4, then H2CO4 is the reactant in excess and aminophore minus is the limiting reactant. To calculate the volume of CO2 that should be obtained, we should calculate first the number of mole of CO2 that should be obtained. According to stoichiometry of the reaction or stoichiometric ratio, number of mole CO2 over 10 equal N0 aminophore minus over 2. We calculate the product using the limiting reactant aminophore minus. Then number of mole of CO2 equal 10 times N0 aminophore minus over 2 equal 10 times number of mole of N0 aminophore minus equal 10 minus 3 over 2 equal 5 10 minus 3 mole. This is the number of mole of CO2 that should be obtained, the maximum number of mole of CO2 that should be obtained at end of the reaction. Then volume of CO2 equal number of mole times Vm, 5 10 minus 3 times Vm 24 liter per mole given, equal 0.12 liter or 120 milliliter. We multiply by 1000 to transform the unit from liter to milliliter. Yield of the reaction equal volume, because since the given is volume and the calculated is volume, then we use the relation volume over volume. Volume of CO2 experimental over volume of CO2 theoretical times 100, since we need to calculate the percent yield, equal experimental volume given 110, theoretical calculated 120 times 100 equal 91.66%. This is the end of the part stoichiometry and chemical calculation.